Hi there, my name is Sarah Wilson and welcome to this tutorial on how to analyze a data file from a tensile test. So we're going to take a look specifically at the kind of data file that comes from a structural stress analyzer machine. The data comes out is force and displacement, and I'm going to show you today how to create the stress strain curve from that data. So first off, over here on the side you can see I've got an aluminum and a brass file, and I think we'll work with the brass file today just because I think that sounds good. You might be tempted to double click right on the brass file, but instead you actually need to have Excel open first. And we're going to choose to open the brass file, and if it's not showing up at first, you might need to enable it to show all files, not just Excel files. And choose that. And then Excel goes, whoa, wait a minute. This is not a normal Excel file. How do you actually want me to open this? So in this little wizard here, this import wizard, if you click on the next button, it takes you to this screen and it says what's separating your data. So you can see down below I'm having two values here. I'm going to have my displacement and my force, and they're separated by a comma. So I'll check the comma, and then you can click next, but you don't really need to. There's nothing on the next screen you need to set up. All you have to do is click finish, and it opens up the data into two separate columns. Now I'm going to go ahead and zoom in so you guys can see this a little bit better. I'll go to 150, I think. And what you're looking at is displacement and force. But the displacement that we have is not just in inches or something like that. We didn't have a sample that displaced, 17 inches or something along those lines. So what you have is our displacement, but we're in thousandths of an inch right now. So to actually make this into the real number version of our displacement, I'm going to add a column. So that was a two-finger click, insert a column, and we'll put our actual displacement here. So I'm going to say I want this column to equal the number that's over in the column to the right, but divided by 1,000. Now you can't really tell that it did anything with the zero. But if you come over here to the right-hand corner, where it becomes a little black cross, and then drag down, what you'll see is that it takes every value from this first column and changes it into the tenths, hundredths, thousandths place version of the number that's on the left. So I'm going to actually copy this all the way down. And, oh, wait a second now. I could copy it all the way down, but you'll notice that after about 71, the numbers over here in this column get very, very small, and they just kind of bounce back and forth between 2 and 3. And what you have going on here is this is after our sample actually broke. So beyond this point, we don't really need any of the rest of the data. So to keep things simple and cleaned up, I'm going to highlight everything here and just get rid of these. Any day now, we'll get to the bottom. There it is. Okay. Now watch out, don't just hit delete. You actually have to do a two-finger click or a right click and clear contents. There we go. So now we've got our data, and it ends right after the sample has broken. Okay. Let's put some labels on these. I don't really need this first column anymore, but I'm not going to delete it just because I don't want to take the time to do it. This column is displacement, now in plain old inches. And this column is force, measured in pounds. Okay. Now this column, these two columns together can give us a pretty good looking graph if we highlight them. Getting crazy. And choose to make a chart out of them. So all of those are highlighted. Notice I didn't highlight the titles yet, just because I found that sometimes in this Mac version it seems to work a little bit better if I don't highlight the two headings. I'll go up to charts, and I'll choose, I'm going to do a scatter plot, but I think I'll choose a smooth line scatter. So it won't actually show me all the dots. It'll smooth it all out for me. Woo! We get this nice looking graph. Okay, I'm going to get rid of this legend because we don't need it. And let's put some labels on this graph so you can tell what we're looking at. We've got up here in chart layout, if you click along in the purple part of the ribbon, you can see it gives you an option for a chart title. So let's put one up here. This would be a brass tensile test, force versus displacement. Okay, and then let's also put some labels on our axes. So on the horizontal axis, down here on the bottom, these numbers are representing displacement. In inches. And our vertical axis is representing force in pounds. Okay, so with that, we've got a pretty nice looking graph that tells us what's going on with this sample of brass, but the downside of this graph is that it is totally dependent on the size of the sample that we tested. For instance, if we had tested a very large sample of brass, it would definitely take more force to break it, versus if we test a really small sample, it won't take as much force. So the reason we don't just stop once we've got a force and displacement graph is because right now it's too dependent on the size of the sample. So this is just our first step for right now. Rather than leave this graph here while we do some other work, I'm going to do a two-finger click on it, or a right click, and let's move it. We're going to move it and make it a new sheet all its own, and we'll call this force versus displacement. And we're making it a new sheet. So now it's got an area all its own, and you can see down below here, if you go to the bottom of the screen, there's our data, there's our graph. Now plenty of space to do some more work. Alright, so let's pause on this graph for now and go back and talk about the data some more. Force and displacement is all well and good, but what we really want to have on our graph is stress and strain. So let's do those calculations. The very first one, our x, should be the strain. Strain is measured in inches per inch. And the way you get that calculation is by taking the displacement divided by the original length of the sample. So the original testing length of the sample. So wherever the sample has a uniform cross-sectional area. All right, to do this formula, I'm going to say everything in this column equals the displacement divided by the original length of the sample. Now, I don't have that on this screen anywhere because we took the measurements ahead of time before we actually broke the sample. And for my particular sample, it had it had an original length of 0.75 inches, or 3/4 of an inch. Now for yours, you definitely will have another number in there, or I guess you might have another number, depending on what kind of sample you broke. So that is the formula that my particular sample needs, because this number right here, the 0.75, is the original length of the testing area. So I hit enter, and again, because it's a 0, it doesn't look like it did anything. But once you drag this down to fill in all the rest of the column, it gives us a heck of a lot of numbers. And yeah, alright, a lot of those numbers could use some rounding. So let's do a little formatting and keep this looking neat. We're going to go up here to Format, Cells, and tell it that these are all numbers, and I really only want to see, let's go to 3 decimal places, and say OK. And that looks pretty darn good now. Now we've got nice, uniformly rounded data. I like it. Okay, so that's strain. Our other value that we want to graph is stress. Stress is force divided by the original cross-sectional area. It's measured in PSI, or pounds per square inch. And we get that calculation by taking the amount of force that the sample was feeling at that particular time divided by the original cross-sectional area. And this is another one of those numbers that we measured and calculated ahead of time. We took out the calipers and measured the skinniest part of the sample. So the place where the brass was the thinnest had a diameter of 0.125, and if you do the calculation with that, you get a cross-sectional area of 0.012 square inches. So I'm going to take every value in this force column and divide by the original cross-sectional area, which is 0.012 for my particular sample. Okay, and just like last time, we turn the cursor to the little black cross and drag it down. Okay. Same problem as last time. We're rounded to lots and lots of different decimal places. So let's go ahead and change this up. We'll format the cells. And this is another number setting. But I don't really want any decimal places this time. In fact, I think I'd kind of like it to just round to the nearest whole number. And so I'll say OK. And that looks a little bit better. And the stress numbers are generally fairly high, so as a result, we don't really need any decimals on them. Okay, so now we've got stress and strain. Let's make one other graph. I'm going to highlight these two columns again. And notice that I'm not highlighting the headings. There we go. And just like last time, we'll do a scatter plot with a smooth line. Hey, that looks kind of familiar. Now you might be thinking to yourself, didn't we just make this graph? And it's true that it's going to look very similar to the graph we made with force and displacement. There is a major difference though. Take a look at that little one we just made, and now compare that to the original one that we made, force and displacement. You should be noticing a major difference. And take one more look and see if you can tell the difference. If your eyes are focusing on that blue line, then you're looking in the wrong spot. Because it's true, the shape of the graph is exactly the same. The difference is the scales. This graph right here, because we converted to stress and strain, should be the same for every brass sample, no matter how big or small the sample was that you tested. Whether you broke it in a small high school machine or one that was at a college where you could break a sample that was, half an inch thick. Overall, the numbers for brass should be fairly constant across the board. Now, I will give you a disclaimer right now and say that this particular test was done on my machine after it had done some traveling and it hadn't been recalibrated yet. So I'm thinking the numbers might be a little bit high for brass. I don't memorize them, so I can't remember what kind of numbers we should be getting, but I'm thinking that these are a little bit high. So my disclaimer is, use this tutorial to teach you how to get these calculations done. Don't necessarily rely on them as an answer key. Okay, so just like last time, we need to go put some labels on this chart. And if you remember, that's up in chart layout. Let's put a title up there. And this time we can call it brass tensile test stress versus strain. Is that what we called it last time? Yep, pretty close. Okay, let's put some axes on there. The horizontal axis now represents strain in inches per inch. And the vertical axis now represents stress in PSI. Whoops. There we go. And just like before, let's go ahead and move this chart to its own page so it has plenty of space. And this one will be stress versus strain. Oh no, I just crashed Excel. Okay, well, I think you got enough of the idea about what's going on here. So the next video that comes after this will actually teach you about how to analyze the graph that we just got from the stress-strain curve. So how do you find all the different points on it that tell you information about how brass behaves in different situations. So check out the next video to learn about how to do some calculations and what all the different points on that graph mean. Alright, I hope this has been helpful, and I guess at least it crashed at the end, right?